Hey guys, today we'll be discussing the volume of solids of revolution using the disk and washer method. The disk method is used to find the volume of a solid rotated around an axis. As you can see in the figure on the bottom left, there's a two-dimensional graph of the area between two functions. As you look to the right, you can see that the 2D shape can be rotated or spun in a circle around a line we call the axis of rotation. In this case, the purple area is rotated around y equals 0, also known as the x-axis. Keep in mind that the figure on the far right looks like a series of circles or disks stacked together to form a solid 3D shape. On the left side of the slide are two formulas that must be memorized. Both equations follow a similar pattern involving the integral of pi times something squared. Many of you may recognize this as similar to the pi r squared formula we use to find the area of a circle. By integrating a similar formula, it's as if we are finding the area of several circles over a specified range that are squished together to form a solid 3D object, as stated previously in the presentation. However, to find the something or area that needs to be integrated, we have to determine the radius of the shape. To find the radius using the first formula, the function on the bottom must be subtracted from the function on the top. You would use the first formula if your shape was meant to rotate around a horizontal axis. To find this radius using the second formula, the function on the left must be subtracted by the function on the right. You would use the second formula if your area or shape was meant to rotate around a vertical axis. Note, the second formula is in terms of dy, therefore all functions must be written in terms of y. After finding the area you need to integrate, simply plug your equation into the appropriate formula. The bounds will be given to you in the problem. Note, as you will see in the following example problems, the bounds will change when switching between using the integral in terms of x versus the 1 in terms of y. Let's try an example. Finding the volume of the solid when y equals square root x when it's rotated around the x-axis from x equals 0 to x equals 4. In order to find the radius of the solid, we will have to subtract the bottom function from the top function. In this case, it's y equals square root x minus the x-axis, y equals 0. We will now integrate the radius squared with the bound specified in the problem and multiply that by pi to get an answer of 8 pi. But how would things be different if we rotated a solid around the y-axis? First, we must solve the function for x in terms of y. For this problem, solving y equals square root x for x would get x equals y squared. We would then have to change the bounds to ones on the y-axis, x equals 0 and x equals 2. To find the radius, we now have to subtract the left function from the right function. Now it's x equals y squared minus the y-axis, x equals 0. Lastly, we would integrate the radius squared from x equals 0 to x equals 2 and multiply by pi to get an answer of 6.4 pi. Not all functions line up perfectly with the axis of rotation. For this reason, there is a method of integration similar to the disk method called the washer method. The washer method is used to find the volume of a hollow solid of rotation. This formula is displayed at the bottom. Finding the volume using the washer method is very similar to finding the area between concentric circles where you must multiply pi times the radius of the bigger circle squared minus pi times the radius of the small circle squared. This corresponds to the integral formula when you have the integral from a to b, some numbers, of big R squared, which is the outer function, minus little r squared, which is the inner function of the shape. In example 1, we are rotating the area between square root x and 1/2 x from x equals 0 to x equals 4 around the x-axis. Here the washer method must be used since 1/2 x is always between square root x and the x-axis for the bounds given. First, we determine the outside function, big R, which happens to be square root x in this problem. So we must do top minus bottom to find the area between the function and the axis of rotation. And since the bottom part is 0, we can just plug in square root x into the formula. Then we determine the 1/2 x is inside the function, or little r, So once again, we do top minus bottom, and the bottom is 0, so we can just plug 1/2 x into the formula. From there, it is just a matter of simplifying the integral, and we end up with x minus 1/4 x squared. The antiderivatives are found, and the bounds are substituted into the equation, which is then simplified to 8 pi minus 16 pi divided by 3. Just like in example 1, we are rotating the area between square root x and 1/2 x from x equals 0 to x equals 4, but instead we are rotating around the line y equals -4. So first we must find the length of the big R by taking the outside function, which is square root x, and subtracting the axis, so big R would be square root x minus -4, or square root x plus 4. The same process happens with little r, with the top function minus the bottom function. So little r is 1/2 x minus -4, or 1/2 x plus 4. So both of these are then substituted into the formula, which is then simplified until you reach -x squared over 4 minus 3x plus 8x to the power 1/2. The antiderivative is then found, and the bounds are substituted into the equation and then simplified until the answer of 112 pi divided by 3 minus 24 pi is read. Thanks so much for watching our video. We hope it has helped clarify the topic and resolve any questions you may have had. See you all next time. No, it's fine. You can always edit the